In terms of priming and motor plans, I also wanted to share with you some work that I've actually done myself during my graduate years. And this study that tell you about is what we ended up referring to as hand pad priming. The idea here is that I've already been talking about how actions rely on plans. And we've also talked about sequencing already. So, what happens when we make a sequence of movements rather than just one movement? The idea in this study that we had was that our own preceding movements may actually, in some ways, prime subsequent movements. And that would be interesting because if that's the case, it would mean that, first of all, there's a plan behind these movements that we can actually sort of reuse from one movement to the next. And it may even be that we can show that movements are not just planned for the sake of being biomechanically efficient or energetically efficient, but that they have to be cognitively efficient as well. And what I mean by that is that if you have an existing movement plan, and that movement plan by and large does the job for the next movement, perhaps we kind of reuse that plan and just tweak it a little bit so that now it gets us by for the next movement, even if that may not be the most energetic way of performing that next movement. We save by not having to redo planning that we've already done, and instead just use that plan, tweak it, and then use that for the next movement. Now, to look at that question, we came up with a pretty ridiculous task where people had to sit behind a table, and as you see, they held a dowel, and there were a bunch of targets on the table, and their task was just to move from target to target in time with a metronome. So the metronome would go like this, and on each tap, they had to hit a different target. So tap, 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 and you see sometimes there was an obstacle between some of those target pairs, and their task was just to clear over the obstacle, not to go around it, but clear the obstacle and then continue the movement sequence. So that was the task. Start at the rightmost target, just keep going back and forth between those targets. When they got to the left, they just started moving back. They did a couple of back and forth cycles. They made one movement every 600 milliseconds, so pretty comfortable pace. And then what we manipulated was two things. First of all, whether an obstacle was present or not, actually three things. Second, where that obstacle was positioned, so it could be between any of those target pairs. And then third, we also played around with the height of the obstacle, so that sometimes the obstacle was reasonably high, 21 centimeters, sometimes it was fairly low. What was the reason for doing this? Well, we were not interested, obviously, in whether people would move higher when they would move over the obstacle, but we were interested in whether that obstacle actually changed the movements they made before clearing the obstacle and the movements they made after clearing the obstacle. And I already mentioned, it may be that when people perform a sequence of fairly similar movements, like they do here, right? Little hopping movement, hopping movement, hopping movement, bigger hopping movement, but still a hopping movement, and then another hopping movement. Maybe rather than planning each of those movements separately, what people do is that they have an existing movement plan from a movement over here, tweak that plan to get over the obstacle, and then again tweak that plan for the next movement. And if that's the case, it may be that when people have cleared the obstacle, they continue to move needlessly high from a biomechanical perspective, but it is because they're reusing that existing movement plan. So to measure that, what we took as a measure is the peak height above baseline. The baseline condition was where there was no obstacle at all, and we got a measurement of how high they moved the dowel for each of those targets. So when no obstacle is present, we know exactly how high they're moving. And then we compared those readings to cases when they did clear the obstacle. If we now subtract those two numbers, if they're moving exactly the same, the difference will be 0. If they move higher, then it should be some positive number. What did we find? So here's a plot of a case where the obstacle is in the rightmost position, but it turns out this result happened everywhere across the workspace. First movement is over the obstacle, so that's not an interesting difference because of course people moved higher when they cleared the obstacle than when they didn't. But interestingly enough, for the movement afterwards, you see that especially depending on the height of the obstacle, for high obstacles, people moved about 5 centimeters higher than they did compared to baseline in that exact same condition when there was no obstacle. And you see that it scales with the height of the obstacle. The second movement after the obstacle is still higher, still higher, still higher, and gradually it kind of fades out. But there's this after effect where people are moving needlessly high. There's no obstacle present there, yet from having moved high over this obstacle, they seem to be reusing that existing movement plan and just slightly tweaking it. Now, then came along a very smart researcher by the name of Peter Streck. I presented him with this work, and he said, yes, that's interesting, but, and that's of course always the but isn't this just elastic properties of the muscles in your arm? So our muscles are elastic in nature, just like a tennis ball is. Imagine if you drop a tennis ball from some height. What happens to the ball when it hits the ground? Well, it's going to bounce, right? Because the tennis ball, just like our muscles, has elastic properties. The higher you throw the tennis ball from, the higher it's going to bounce. So this whole effect here may just be a biomechanical effect where the same arm muscle is being used, and this is nothing more than just the arm muscle bouncing in the same way that a tennis ball would. So I remember that day and I thought, oh crap, am I even studying psychology here, or is this just biomechanics? Well, fortunately, Peter Strick was also smart enough to immediately provide me with a way of testing that possibility versus the reuse of movement plan. And here's what he suggested, which was very smart. Change the task by one little thing. One arm moves over the obstacle, the next target over, the left arm then continues the movement sequence, goes all the way to the end, all the way up here until you get to this dot, and then the right arm again moves over the obstacle. So now there's one arm that's moving over the obstacle and the other arm is just doing the continuation movements. If it's biomechanical in nature, now you shouldn't see an after effect anymore. If it's the reuse of movement plans, then it should be that you can transfer a plan from your right arm to the left arm and you may still see an after effect. And as you can tell in this plot right here, that is what we actually found. So indeed, people continue to move excessively high, even when they cleared with their right hand and then switched to their left hand. And for the other hand, it was the same pattern. So this suggests that there is in fact plans that are being used and reused. Motor programming, we concluded, is largely achieved by changing those features that distinguish the next movement to be made from the movement that was just made. And that's cognitively efficient because it avoids a lot of redundant computation, right? You have a movement plan that pretty much does the job. Rather than deleting that plan and then calculating a very similar plan, we can just use what we have and then tweak it so that it's very efficient, cognitively speaking. Even if biomechanically we do a little bit more, we spend a little more energy, cognitively we save a bunch. And what's interesting about this also from a psychological perspective then is that obviously that action planning is not just about acting in energetically efficient ways. It's also about acting in cognitively efficient ways. Now, does this sort of planning like this just happen for sequences of continuous movements? Well, actually, it turns out that that's not the case. There's plans involved in discrete movements as well. And one way to show this, well, first of all, you can do this for yourself at home if you want to. If you want to do this, you can grab a bunch of plastic cups or paper cups and put some of them upright and then some of them upside down. And then after you've done that, you can pretend to be a waiter or waitress who is going to fill these cups with a pitcher of water. So you have a pitcher in your left hand, and now you're going to use your right hand to pick up those cups one at a time, fill them with water and put them on the table. And what you'll notice is that for the upright cups, it's very straightforward. You have a very easy grasp. Your hand is in a normal position and you just pour the water in. For the cups that are upside down, you will notice that you're actually rotating your hand so that it's basically inverted when you grab the cup, and then as you have the cup in your hand, you rotate the cup so that it's now upright and you're now in a comfortable position. This was demonstrated experimentally, and it was coined the end state comfort effect. And the idea is that we plan our actions in some ways relative to the comfort we have at the goal of the action, so at the outcome. So you can see it here, and this was actually an effect that was discovered by the author of the textbook we're using, David Rosenbaum. If you put a dowel with a black end and a white end on two little, what do you call those? Well, two little pieces here that it's elevated from the table. There's a target on the left and a target on the right. Okay. People are then given the task to reach the dowel with their right hand. And for example, they're told to put the black end to the target on the right. Now, if you do that, you will notice that if you try that for yourself, you'll actually use an underhand grip to grab the dowel so that you can then rotate it and end with your hand upright on the target with the black end down. So you're using an underhand grip. If you're doing the exact same task, but now you're being told use your right hand to put the white end on the target on the right, you'll use an overhand grip. And as you can see, right, if you hate statistics, this is a great experiment because they tested 11 people and every single one of the 11 people did exactly what you would expect based on end-state comfort planning. They grabbed the object, the dowel, in a relatively uncomfortable position if they needed to then end up comfortably. That's the end-state comfort effect. You get the same sort of effect when you do the following task. In this case, there's a toilet plunger, a clean one, on some starting platform. And you see that there's some sort of target platform that the plunger needs to be moved to. And in the next images, I want you to watch where that target platform is and then where the hand is positioned on this plunger. And I'll just go back and forth a little bit. And I've been told that this is kind of vulgar, but you see that as the height of the target is changing, the location of the grasp on the plunger is also changing in such a way that the plunger is being grasped in a relatively high spot when the target is low in order to avoid having to bend down a ton. And the plunger is grabbed in a low spot when the target location is relatively high. So again, people are changing their grasp, their initial grasp on the object in anticipation of what their end state is going to be like. Now imagine if they grab the plunger right here for a high shelf, you would end up very uncomfortably and having to reach very, very high. So it is very smart in some ways that our system is correcting for that and adjusting the grasp height depending on the height of the target. And if you plot this in a formal way, you see indeed that there's a very nice linear relationship, an inverse linear relationship, right? As one goes up, the other one goes down. As the height of the target platform increases, the location of the grasp on the plunger decreases. And what this does is that you end up relatively comfortably. So this grasp height effect and the end-state comfort effect suggest that people use action plans where they anticipate their end posture, the way they end the action, and then from those goal states, they work back to figure out which initial states to adopt so that they actually end the movement comfortably at the goal. All of this stuff clearly suggests that plans are involved in actions. People rely on plans when they perform actions, and those plans are not just about minimizing energy expenditure, they're also about being cognitively efficient. And this also establishes indeed that action planning is an important domain for psychologists to look at. It's not just biomechanics, physical therapists who need to look at this. A lot of action planning is actually psychological in nature. This makes sense if you look at the definition of psychology, the study of mental life and behavior. Action cognition and action planning are all about the actual behavioral output that people produce.